Welcome to the second lecture in the Wireless Distinguished Seminar Series. Today, it's our greatest honor to have Dr. Peter Wedder with us. Dr. Wedder has recently been nominated President of Bell Labs Co-Research at Nokia and is a Bell Labs Fellow. He's leading a global research organization with the mission to invent game-changing innovations that define the future of networks, including network systems, security, optical systems, radio systems, platforms, and ASICs. In his previous role as head of Access Research Lab, he and his teams have realized several world-first system demonstrations in access and successfully transferred industry-leading concepts into products. He received his PhD degree from Ghent University in Belgium in 1991, followed by a postdoctoral fellowship at Tohoku University in Japan. He has authored over 100 international papers and presented keynotes and tutorials at major technical industry events. Dr. Wedder, thanks a lot for accepting our invitation, and the floor is yours.
Well, thanks, Yaseman, for inviting me, and the kind introduction and the correct pronunciation of Ghent, my alma mater in Belgium. I'd like to encourage you to turn on your videos if somehow possible, if you don't have kids that need the upstream bandwidth in the house. It's so much more pleasant to talk to an audience. So first, a bit of a comment. It sounds lofty, but President of Bell Labs Core Research, a bit of it happened last week, a bit of context. We've decided to create two Bell Labs organizations, a core research solution, a core Bell Labs research and a solutions research. And the reason for that is that Bell Labs has actually a dual mission. We need to secure the future of the core business, the core technologies in network. And then we also need to go into new pastures, new technologies and new growth opportunities outside the existing core business. And because the market is so dynamic, we felt let's set up two organizations that are closely coupled and two presidents that have each their strength. And I'm happy to lead the core research because that is actually what I've been doing for mobile networks and fixed networks until now, and now do it for the larger core research, which includes also network programmable systems, security systems, and optical networks. So I'm actually very excited that my first public talk as that leader of the Bell Labs core research is to Princeton, a prominent research university right in our backyard, and I hope it is the start of or a continuation of the collaborations that we have with you. What I chose to talk about is to talk about our vision of 6G, how that will, and I hope you can see this, how that will augment the human potential. And you see how that morphs into a brain here, this animation, so augmenting our intelligence, but also augmenting our knowledge, the way we handle knowledge, our proximity, and our productivity at large. The reason why we talk first about in 6G about augmenting the human potential is when you talk about 6G technology, you have to have a vision in mind, what will be the applications that these technologies will be designed for. And so in Bell Labs, it's always very important, what is the big human need problem, and then what are the 6G era network technologies, and so there will be two parts in that talk that I have here. So augmenting human potential. First, proximity. So this is inspired by a book of Harari, Homo sapiens, that basically makes the point that our brains and our capabilities have been optimized through evolution to become a hunter-gatherer. But our environment over the past thousands of years has changed a lot to the human urban consumer, but our human capabilities have not evolved in the same way. So the number of people that the hunter-gatherer interacted with was 150. That was pretty much the total number of people that the hunter-gatherer would meet in a lifetime. And so our brains are very well wired to collaborate with 150 people. As soon as it gets more, it gets inefficient, complicated. But there are organizations, cities, companies, universities that you easily get into 10 to 100,000 people. In Nokia, we have 100,000 people are an email click away from you. But these are not the same resonant collaborations that you can have with a team of 100 and 150 people. So it increased diabolically to 100,000. You see how I, with these numbers, play a bit with the number 6, since it's about 6G. The density of population also increased by 600. In New Jersey, we have more than 1,200 people per square mile. And you know also, the whole globe is within reach. There's only 6 degrees of separation. I reckon actually in our profession, we are probably only 2 or 3 degrees apart, if you look at it. So we need help to improve our proximity. The other thing is intelligence. So the ability to understand knowledge, to reason, to collect information. And also there, things have changed a lot from the times of the hunter-gatherer. In the times of the hunter-gatherer, knowledge pretty much stayed constant. These are the fruits that you can eat. This bear is dangerous. You can fish there at the river. And that was pretty much the knowledge that the hunter-gatherer needed, and that was fairly constant. But since the Renaissance, our knowledge increased, and the period that it doubled, it's more than exponential. The period that it doubled shortened and shortened and shortened. In the times of the industrial revolutions, it was half a century. It shortened to a decade. Just 5 years ago, it was every year, and now we are at a pace of doubling every 12 hours. That the knowledge, not the information, learned experience is doubling every 12 hours. So as humans, we need help, because with this curve, the Ebbinghaus forgetting curve, is our brain. Pretty much everything I tell you, most of it in a month from now, you will have forgotten. So we need help. And the good thing about having that you forget is that I can get to reuse slides. You maybe have seen me give it keynotes at conference, and I've used some of these slides, but I can present them again, and you may still find them interesting. And this is a slide that also Marcus Weldon has presented quite a lot on productivity. He basically makes the point that our ability, our productivity measure, and that is growth has increased over the past, in the first half of the past century. This is from a book of Robert Gordon, Rise and Fall of American Growth, and it raised from 1% to more than 3%, thanks to inventions in the Industrial Revolution, Second Industrial Revolution, transportation, chemistry, power grid, and telecommunications. But then in the second half, the productivity decreased, growth decreased again, despite the invention of mobile networks, despite the invention of the internet. And so the question is, why is that? And Marcus Weldon would joke, it's because we've been using the network to exchange pictures and videos of cats and dogs. We've been using the internet just for shopping, so it's moving value around, it's not really productive. And the whole point of presenting that slide is we need to bring the ICT technology and the 5G technologies to the industry to enhance our productivity. And we start seeing that. Actually, since you've seen these slides, COVID happened. And COVID has shown that the network infrastructure is crucial to keep our economy going. Here is a curve on the e-commerce. And in a period of 6 months, the e-commerce has grown to an extent that otherwise would have taken more than 6 years. So it is a proof point that ICT infrastructure is extremely important for our productivity. But this didn't happen overnight. There was actually an investment of infrastructure that happened for more than a decade. And it was thanks to these investments that peak could be handled. And yes, there have been some adjustments, scaling the capacity of Zoom sessions and what have you. But the basic infrastructure was there. But this lesson learned will cause now an acceleration of investment. This realization that you need to enhance the proximity, that you need to do more automation, that you need to be able to work at a distance, will cause an acceleration. So typically when we talk about the automation, we talk about two industries. The digital industries, these are the industries that already embrace the digitalization, e-commerce, banking. And they have the largest investment, 70% of ICT, though they only represent less than 1/3 of the economy. And then that larger part of the economy, the physical industries, think mining, transportation, retail, they have only 20%, 30% of the ICT investments, even though they are the largest part of the economy. And you see the difference in the economic growth. The digital industries have that healthy, almost 3% productivity growth year over year. The retail and other physical industries, they are at a less than 1% growth. And the whole idea of ICT is now, an industrial automation, is to bring the ICT to these physical industries. And now with the acceleration of, thanks to the realization of COVID, is we will see an acceleration of these investments. And this is an analysis that Bell Labs Consulting has done, my colleagues at Bell Labs Consulting. So you see here the red curve already that I've shown you earlier, the mature e-commerce infrastructure, but then also the physical industries. Think retail, think transportation will have an acceleration, and the inflection point will accelerate by 3 years. And even the laggards, think agriculture, they also will have already their inflection point in this decade. And so here you see that inversion of the ICT investment now in the physical industries, more than 2/3, and really more representative of the size of these respective economies, digital and physical industries. Now, it's also important, this talk is about 6G, that these investments happen before 2030 to a large extent. So these are still 5G technologies. And so the big question is, what will be the 6G new applications that we need to think about? And so for that, it is good to look also a bit at the history. Every generation has optimized the use cases of the previous generation and then had a defining new application and use case that set the direction of the inspired the research and set the direction of the standardization. And so 2G was about voice, 3G optimized the voice for cost and enabled internet and data access. 4G enabled lower cost, higher speed internet data access. Voice basically became zero cost and started enabling video. And now 5G optimized for video. Now we can have interactive video over 5G. And the new use case was industrial IoT, enabling this industrial automation. So in 6G, these use cases will continue to be important, but the new uses for 6G, well, it's still crystal ball looking, but it will likely be all around massive scale deployment of sensors, massive scale deployment of AI in new ways. And that allows us to really connect the physical worlds with the digital worlds and automate our productivity in more efficient ways. And I'll explain that a bit more, but in the theme of the proximity intelligence and productivity, we can say that most of the previous generations have enhanced proximity. Proximity between humans, proximity to data. 5G for the first time really addressed the productivity question, dual digital industries. And then in 6G, we can expect that we will enhance human and augment human intelligence. So here is another way of looking at that. So in 5G, we connected humans and machines to enhance the productivity. And now in 6G, thanks to the massive scale deployment of sensing, we connect the physical world in a much richer way with digital twin models in the digital world. And same for our human biological world. in a much richer way. And why are these digital twin models so important? Well, they are actually the perfect knowledge engine to model possible outcomes, to get a state of what's happening in real time, and then take decisions, anticipate needs, take actions back into the physical world. It also allows to transport these digital twin models. I can bring these digital twin models in real time and be there with you as if I were there. Or we can transport these digital twin models and you can then 3D print them in a different location. So connecting digital worlds with physical worlds and biological worlds. Now, to some extent, this is already happening today. We have digital twinning in factories, keeping the state of machines in industrial automation. Increasingly, 5G is doing that also in a wide area network in smart cities, digital twins of smart cities. And there are some precursors of digital twins of ourselves. Think of a Fitbit and a health app, or your file at the GP. But in the future, we can expect this to happen more in real time with new ways of that. Now, this massive scale deployment of sensors, this massive scale deployment of intelligence will have an enormous impact on our future network architecture. You see here a simplified representation of the network with the access network, the anyhow, the edge cloud with the embedded intelligence capabilities and the IP transport and the centralized cloud. And so the massive scale deployment of sensors will cause a lot of upstream capacity, this new killer app, if you want, to these digital twin models. And you can think of these digital twin models as, 3D representation, 4D if you add time, and then multiple layers of parametric information. But you can also think of these as more abstract, self-learned, thanks to AI models that update each other, but also in a distributed way, update weight factors across the different AI platforms. So also that will influence a lot how we design the network. So I'll illustrate that power of the digital twins and how that augments our productivity in 2 years. So first, the intelligent farming. So vertical farming, actually with a partner here in New Jersey, in Era Farms, we are enhancing the proximity. We are repurposing, so that's the idea, of repurposing warehouses so that the produce is grown closer to the consumers. So you reduce basically the transportation time. You have fresh produce by an average of 5 days, and you also repurpose the space. And it enhances the productivity because you can optimize the use of water, inject them really at the root of the crops. You reduce the growth from 40 days to 12 days, thanks to the enhanced lighting. And the whole productivity actually improves by more than 300, thanks to the vertical stacking, the optimal use of fertilizers. And then it's actually also with zero pesticides because it's an almost contamination-free environment. So in order to understand this better, we have actually built our own little vertical farm in Bell Labs in Murray Hill in New Jersey. You see it here on the upper right. And then on the right-hand side, you see a simplified digital twin of that. And you see a drone flying in between those shelves, and that is to monitor the growth of the crops. And so there is already wireless connectivity and localization happening. You see on the left, bottom right, the fish eye view of that drone. And so the drone, thanks to centralized control, is now following a predefined path that you see on the right-hand side with the green line. And it's almost perfectly following that path. So that is one aspect of autonomous control. The other aspect is then we do this to inspect the crops. And you see here a view of the shelves, the drone flying across them. On the upper left side, you see the raw video. On the lower left, you see a leaf segmentation that is happening in real time. On the upper right, you then see how there is growth inspection by looking at the color And then at the lower right is inspecting the growth by doing classification of the images. So this is one example how we augment our capabilities to enhance the productivity thanks to these new technologies.
Peter, can I ask a question? Sure. Sure. This is actually very interesting. So there's one aspect to it, which is reduction of water. How about like reduction of carbon footprint, in the sense that are the lights being also sort of replacing sunlight in some way? So are those powered by solar or renewable energy, or how does that?
So without knowing the details of how our partner Aerofarms does this, but yes, these are LED lights which are most optimal, and you can indeed imagine an optimization algorithm where on one hand you have as a constraint sustainability and carbon footprint impact. On the other hand, you do want to have the most optimal growth. So I can imagine then algorithms optimizing for that problem and using the rich set of sensor inputs to make that happen.
Okay, all right, thanks.
So I'm going to back in sharing mode. I had to stop because there was another video that started. Can you see this well? So the other example that I want to share with you is that happens is the intelligent factory. So we fly our own jets. This is our factory where we built our radio systems in Oulu in Finland, where we apply some of these digital twin models and 5G industrial automation concepts. And you see in this factory, there's still people there, but they're not doing the manual tasks anymore. This is all automated. These people are there to do the more complex monitoring, product optimization, injecting creative new solutions. All the rest is fully autonomous. And making that happen, is actually really enhancing the way that we can reduce the lead time by 80%. The other important outcome that we have realized by introducing these concepts is that we have a enhanced productivity of more than 30%. And because we take humans out of the loop for the inspection, for instance, of solder joints and how printed circuit boards are built, we have half the defects because we take the human out of the loop. So overall, an enhancement of the quality also. So these are two examples, Aerofarms and then manufacturing, where we use the power of digital twin as the perfect knowledge engine to enhance productivity and augment our human capabilities. So another way of looking at this is we augment our proximity. So back to the theme that I started in the introduction. So our ability to sense at a distance, to sensors modalities that our human senses are not able to have, to act at a distance, for instance, also in hazardous environments, and to represent ourselves at a distance. Hopefully future in a more 3D immersive experience than we have it today. Second thing is then on augmenting our intelligence. So what we sense, understanding that, anticipating needs, simulating possible outcomes, and then plan decisions, plan actions back into the physical world to enhance our productivity, the third dimension of the themes that I introduced. So why do we do this? To offload humans with things that machines simply do best, manual tasks, or also tasks like hashing through thousands of images for quality inspection. But then also augment humans to do what humans are best at, say, taking care of other people, learning, solving more complex problems, being creative. And these are typically then also the things that people mostly enjoy. So to make that future happen, so these were more the application aspects of the 6G era, we expect important changes in the 6G network infrastructure. And I want to make the point that many of these aspects already happen in an early phase today in 5G that I mentioned. But 6G will make this happen at a much larger scale with much higher precision. So you see here the 6 research vectors that we are pursuing. In 6G, there must be 6. AI, ML, air interface. And I have a slide on each one of these. So native AI, ML, air interface. New spectrum technologies, in existing spectrum as well as in new spectral bands. And then not only for communication, but using that ubiquitous availability of radio infrastructure also as a sensor. And all that needs to happen with security and trust. If you communicate a digital twin, you don't want that digital twin to be hampered with. Extreme connectivity with even more extreme requirements than what we have today with ultra reliable low latency communication in 5G, but in very specialized specific areas. And then these are a lot of examples more on the, I would say, physical layer, the radio communication part, but there's an important new paradigm also to be looked at in architecture innovations. So I have a slide on each one of these to make you understand how we think of this. So an AI, ML native air interface. So communication between A and B over a channel, we came up with the well-known model of transmitter and receiver with the well-known functional block of front-end modulation, error coding, and scheduling. And already today, we see research and first prototypes of using AI ML in 5G to optimize for these individual functional blocks. In 6G, the native AI ML interface is take a clean slate, do away with these different functional blocks, and let the 2 endpoints in real time figure out how to optimize in the most optimal way. And we've done already first experiments on that, where an AI/ML air interface, depending on the channel conditions, figured out what is the most optimal constellation to communicate. And it's no longer that classical QAM constellation. And this approach will reduce the complexity and change the way we design radio systems. It will also change the way we define standards. Second is new spectrum technologies. We can expect that the existing 5G bands will be repurposed for 6G as we progress. Millimeter wave, the mid-band, and the low band. But there will be also new bands. So there's a lot of research excitement already in the terahertz range. Terahertz with even more bandwidth, new research challenges, and then also sensing capabilities that I will talk about later. But even less than millimeter wave, it is limited in the range. So you see at the bottom here the scale of the range. These near terahertz bands have a 100-meter range, and we can expect that this will be mostly an indoor capability. Another important band, which is less addressed in the research community, but it is equally important, is the band just above the midband, where there is an opportunity to design new radio systems that can still be deployed from existing cell sites. We've learned again and again in mobile networks, if you can deploy it from an existing cell site, you will deploy it from an existing cell site. We can dream about small cells, but that rollout goes slower than expected. So also in the 6G era, if you can leverage high capacity, but get a better range than millimeter wave, and think of new massive MIMO systems with a long reach, definitely an area of research. And then we can also expect new spectrum capabilities in the low band to really get to very high, large coverage.
Peter, can I ask a question about the new spectrum technologies? So the question I have is that what do you specifically mean by technology? So is this physical layer? Is it is modulation encoding mature, or is there room there? Is it just about massive MIMO? Are access technologies part of the picture? Is multi-hop part of the picture? So I'm just wondering, as you think about the new technologies here, where is the most important research to be done, or is it across all areas of technologies and all bands?
It's across all areas, but a very good question. I would say, for instance, in these sub-terahertz bands, it's really about new waveforms. Is OFDM still the right thing to use there? I think in this new golden band from existing cell site, it's massive MIMO. But massive MIMO with even larger antenna arrays, probably to still get to that long reach. But then, yes, there are these challenges as angular spread. Does massive MIMO and the simple beamforming that we have today help us, or do we need more complicated conjugate beamforming to really get the benefits of those large arrays in scattering environments? And then with that, conjugate beamforming, enormous processing power that we need. So are there ways to simplify that? And this is a call also to the SoC and processor people. Help us to think of future processors to do this in an energy efficient way. And then, it's not only about the communication, but enabling then also the sensing. So the waveforms need to support simultaneous sensing. And we're already using the radio as a sensor today. You see the video here. This is in an experimental factory in Stuttgart, in Germany, at Arena 2036, where we collaborate with different industry partners. And we are doing a real-time tracking of this robot moving around using 5G with 10 centimeter accuracy. And you see here how that diagram is tracking the motion path of the robot. And just for clarity, in the previous picture, you've seen that same robot in our Nokia factory. That robot was still using optical. It was still following strip lines on the ground. Here, this robot is truly using only 5G as localization method. So there's no optical localization involved here. It's not following the lines on the floor anymore. But now moving to 6G and having wider bands, we can do sensing in a much richer way. We can use the radar to not only get location information with higher precision, but also volumetric information. We can get material-specific back reflection information, whether it's a body that contains water, is it a mammal, is it a metal surface? So combine that with AI and you get what we call a network with a sixth sense. Then the fourth challenge is extreme networking. So pushing the limits really further in industrial automation to go to 100 microsecond range. But we think of this as critical subnetworks. The endpoint of networks is again a network, the network of networks. It's a machine area network. It can be a car area network. It can be a body area network with very specialized requirements in terms of synchronicity that even can go into the nanosecond range. Latencies within 100 microseconds. And the reliabilities that can go up to 5 nines. Think of a car as a simple example. You don't want the brake to fail, never. So very specialized subnetworks, the network of networks. And then it's also about new network architectures. We already see the paradigm shift towards cloud RAN. And we've done research ourselves on enabling radio access network functionality on common off-the-shelf hardware. We've built a distributed unit on a common off-the-shelf GPU. And so doing this in a cloud-native design allows us now to instantiate these functions on a slice-by-slice basis and optimize the placement depending on the latency requirements. And you see, for instance, for a low latency slice, all functions are on the on-premise cloud here in this diagram. Now, going forward, this is just the start of it. You can now think of microservices and do away with the notion of core and RAM and have a fresh look at the partitioning, eliminate redundant function and optimally place these. And not only optimally place the function, but really create functions that are specialized for a specific purpose. A scheduler for low latency is different from a scheduler for high bandwidth. So you can create these specialized instances. And then last but not least, all this needs to happen with security and trust. We understand that there's an enormous threat surface that is inflating. There are billions of devices, untrusted devices. There's millions of these endpoint subnetworks. There's open interfaces with components from different sources. It's running on a heterogeneous cloud, private cloud, web scale cloud, CSP cloud. And then there's also different sources of these microservices from open source, from multiple vendors. There's different software patches. So this is.
Can I ask a question?
Yeah, sure, Steve.
Yeah, so security has been always included as a bullet point for every generation at some level, but as network connectivity has increased and criticality of networks has increased, really the security posture has gotten worse over time. And so unless somebody can build into both 5G and 6G networks and the compute that sits on top of them and an assurance of security, aren't we just setting ourselves up for essentially a superstorm of crime and other types of hazards?
Yeah, no, Stephen, that's exactly the research challenge that we need to address. So it is an untrusted infrastructure, but how can you create a trusted service over an untrusted infrastructure? And we're looking to the likes of you to come up with concepts like, can we have anchors of trust that when data is propagating through the network that you have these intermediate verification points? Can we leverage such concepts as blockchains for authentication of endpoints? Can we leverage AI/ML to analyze? AI/ML is a source of a threat source, but it can also be a tool, the automated generation of software that we then can trust rather than having something implemented by a hacker. So there's different research directions that need to be explored. I've been, actually, this is a good moment to call out the NSF RINGS project. And the R in RINGS stands for resilience, meaning creating a resilient infrastructure that is resilient to security threats. So as a university, I hope you've seen that. I've been involved in the setup, talking to NSF, but yeah, this is an important challenge to be addressed. And this actually brings me to the last slide. So the takeaway is really one, the applications. How do we enhance the human potential in the 6G era by twinning the physical worlds and our own biological worlds with digital twins in the digital world? And this being then the perfect knowledge engine to optimize productivity back into the physical world. So this is the application era for the 6G, and then the new technologies, the 6G vectors that I introduced to you. And with that, we can open it for questions.
Thanks a lot, Peter, for the wonderful talk. I think we have time for a few questions. I start with a question myself. So you talked about sensing and communication, and I think so far when we're thinking about the two, it's either we're talking about the problems associated with coexistence of radar and communication, like a spectral management technologies, or we are talking about passive sensing, where you are repurposing wireless signals for sensing. Of course, you can add machine learning and AI techniques to boost the accuracy. But how does the future of this joint communication and sensing look like in your vision?
Yeah, so it's a good question. We should, however, look broader than just the radio sensing. Radio is just one sensing modality. The benefit of the radio sensing modality is it is ubiquitously around us, and so we can leverage it. But we should combine it with also cameras. Whenever the cameras are there, use it. Radio has the advantage that it's less privacy sensitive, though that may evolve, of course. When you get more information out of the radio, privacy will become an issue. And then there's other sensors, simply human activity in a residential setting, slamming the door, opening the valve. When you have acoustic sensors that pick that up, you can also analyze, okay, this is happening now. The next step that we need to prepare in the home automation is this. So radio is one sensor. It has this unique set of research challenges, but we need to look at the larger picture of other sensors and combine these multiple sensing modalities.
Right, thanks.
If I may ask a question. So you mentioned digital twins, and traditionally digital twins have been for different system components. For example, in the case of a human, it could be a digital twin of the heart or the kidney, or in the case of automotive applications, it could be a motor and so on. And ultimately, one vision could be having a digital twin for the different components and having a system of digital twins that interact with each other. But is it possible that 6G can also enable other types of digital twins for digital twin for human behavior or human decision making? Because we have more data available. So instead of just looking at components, can we now model humans in different ways in terms of behavior, in terms of decision making with 6G technologies?
So absolutely, that is where this is going. So the combination of the digital models, and actually in a way, it is already happening in a precursory way. If you think of what Amazon is doing with your buying behavior, it is keeping a model of you, of your interests, and trying to predict what will you be interested next. You as an individual, but possibly also as a community, so that they can stock up their warehouses properly to reduce the delivery time. And they're probably 90% right already. So this kind of human digital twin model is already happening in it, maybe not in real time, but is happening. Also, Google actually in the search engine, it is keeping track of what are your interests, what are you searching, and then use that model of you as a way of predicting what you will be interested in your next search. So in a way, it is already happening. The other thing that comes to mind when you say that, it is also enabling these digital twins as a platform so that multiple parties can use it and enable as a service new business case. So you on one hand have the infrastructure of sensors, but then you have exposed that capability and deploy it as a service. And in an early stage, again, Google has done that with Google Maps. They provide the infrastructure of Google Maps. They provide the data of traffic. And then you have other companies and apps that make good use of this.
Okay, thank you.
So, I have so many questions as always. This is a really great talk. I guess one question, a high level question I have is, how is this all going to be monetized? I mean, we know how the cellular infrastructure has been supported. If we think about pervasive sensing, if we think about bridging the digital divide, or a lot of the use cases for 6G, is there a different economic model that the carriers are going to have to adopt to make the rollout and the cost worthwhile, or is it just savings through the new technologies or some combinations?
Yeah, we're still doing a bit of crystal ball watching here. I think on one hand, 6G connectivity will be a replacement, and we cannot expect to get more revenues. The the consumers and the industries will expect more bandwidth and more better performance, but not at a high cost. So that is one. But what we do see is that the business models are changing. We see a trend towards more openness with O-RAN, different players that, well, different system and component vendors that need to interact with each other, but then also more openness in the way that the network infrastructure is used. So we see, for instance, already that the web scalers are making their platforms available, and that the CSP, the communications service providers, are using web scale platforms to embed the core functionality. So you do see different business models, and how that value chain then pans out, we still need to see. And then the web scalers, again, have their own, I would say, exposure to API with over-the-top deployment of applications. So a direction that we see is, and I mentioned it already in answering Miraj's question, is these as-a-service deployment models, network as-a-service deployment models. Networks, and including all, so in that infrastructure like sensing and enabling the APIs, and then automating that so that the complexity is shielded, but that it becomes easy for application developers that then create money out of this and value out of it.
Great, thanks so much. I think we're running over time. So thanks a lot for attending. This talk was recorded, we will post it online, and see you next time. Peter, see you in a bit.
Thanks for having me, and looking forward to further discussions.
Yeah, thanks so much, Peter. I'll see you later this afternoon, but thanks for the wonderful, wonderful talk.
Thanks, Peter. I'll see you later too.